intermolecular and intramolecular forces. So we're going to start by filling out a little bit of notes here about our inter and intramolecular forces. The first thing that I want to point out is that we have our intermolecular forces over here on this side, inter. That means between. So if you think of the word like interaction, right, you need two people to interact. So intermolecular, we need two molecules. So inter really means between two different molecules. These are the forces that hold molecules together as a substance. On the other side, we have intra, which means within. So these are really going to be the bonds that hold atoms together into molecules. So we're going to start and we're going to go through each column here and we'll fill in these notes as we go. So first, I want you to take a look at this picture here. So this is showing us two molecules. We have molecule A and we have molecule B. Now, if you look at this picture, it's possible that when these molecules get close together, that our electrons become less evenly distributed. So here we start with very symmetrical electron density. But for whatever reason, these are all bunched up on this side of the molecule. So this side is going to have what we call a partially negative charge, delta minus, partially negative. So delta means change. You're probably familiar with this one. Perhaps in engineering classes, you've encountered that. This is a lowercase delta. So uppercase delta means big change, whereas lowercase delta means small change. So when these molecules get close together, this causes the electron cloud to become skewed. So we have one side of the electron cloud that is partially negative and one side that is partially positive. So for that brief second where my electron clouds are unequal, where they are asymmetrical, for that brief second, these molecules are going to attract to each other. So like little magnets, the negative side of one attracts the positive side of the other. So we're going to have this attractive force. Now the next second, it might go back to being symmetrical, and that attraction is gone. So we have a name for this temporary attraction between molecules. It's called dispersion forces, or it might be called induced dipole. This is where we get these temporarily asymmetrical electron clouds. It makes our molecules temporarily polar. So for that brief moment when those electron clouds are skewed, we have this attraction between the molecules. The next second, this attraction might go away. So this is going to be a very weak attractive force. This occurs in all molecules. So anything that is a covalent compound is going to have dispersion forces present. So if we look at this picture here, these are two molecules that have gotten close together, causing their electron clouds to become skewed, to become distorted. So for a brief moment, we have this temporary attractive force between these two different molecules. The next strongest type is called a dipole-dipole force. And this is very similar to a dispersion force. The only difference being is this is a permanently polar molecule. So this could be something like HCl, where one atom is much more electronegative, pulling electrons to one side of the molecule, and that causes us to have a dipole. So same idea as before, the only difference is these are permanent dipoles, so this attraction is always present, making it a little bit stronger than dispersion forces. But it's the same idea. These atoms have distorted electron clouds. Just as they exist, they have these distorted electron clouds. So one side of that electron cloud is electron poor, forming a delta positive charge, and the other side is electron rich, forming a negative charge. So the only difference here is that this is because of the different electronegativities, and so this is a permanent dipole. So that attractive force is a little bit stronger. So this is going to be present in all polar molecules. And the way that you can tell if something is polar or not is by looking at its 3D shape. That's why we learned about Vesper shapes a couple classes ago. So this happens whenever we have two permanent dipoles on different molecules that are attracting each other. So again, these molecules are like little magnets. The difference here being that in dispersion forces, the attraction is temporary, whereas in dipole-dipole, it is a permanent attraction. The next type of intermolecular force is even stronger, and it still is the same idea. We have these molecules that are partially negative, partially positive, and they attract each other. So hydrogen bond is really a bad name. It would be better to call this a hydrogen attraction, because this water molecule is attracted to a different water molecule. This is confusing to students because when they see hydrogen bond, they think I mean this guy. This isn't a hydrogen bond. This is a covalent bond that happens to be between an oxygen and a hydrogen, but it's not a hydrogen bond. This is a hydrogen bond where we're showing the attraction of one molecule to a completely different molecule. So hydrogen bonding is kind of like a dipole-dipole interaction on steroids. It's just much, much stronger. And this is because we have a very polar bond, a very polar molecule. So this is the attraction of H from one molecule to the FO or N of another molecule. So this is a very, very polar interaction. So this is going to be the strongest intermolecular forces, and this is why water is going to be a liquid at room temperature rather than a gas, because water is really attracted to itself. It's very sticky. So water molecules stick to other water molecules very easily, so we get condensed state of matter like liquid. Now we want to talk about the intramolecular forces. So these are just the bonds that hold together atoms in a molecule. So in a covalent bond, electrons are being shared in a single, double, or triple bond. If they are shared equally, it would be nonpolar. If it were shared unequally, then it would be polar. So an example of this could be hydrogen, H2, and hydrogen fluoride, HF. So H2 is going to have a very symmetrical electron cloud. That's what we have on the screen. If I cut this in half, it's always the same on both sides. So because this is highly symmetrical, the electrons are being shared very equally in this bond. We've got a polar molecule. So this bond here, we have a nonpolar molecule. So this bond here between hydrogens is very even, very equally shared. So it is a nonpolar covalent bond. In a polar covalent bond, that electron cloud is skewed, usually because one of those elements is more electronegative than the other elements. So what this means is that this side of the molecule is going to be partially negative because it's electron rich, whereas this side will be partially negative because it's electron poor. If you cut it in half, we can see that it's asymmetrical. So asymmetrical, a lack of symmetry, if it is without symmetry, that means polar. So the diagram on the page here is showing us a non-polar molecule. The next type of intramolecular force is ionic bond. So in an ionic bond, one atom is going to lose electrons, forming a cation, whereas another atom is going to gain electrons, forming an anion. Usually it's a metal that loses electrons to form the cation and a nonmetal that forms the anion. But remember, we can also have polyatomic ions present too. So these oppositely charged ions are going to attract to each other, forming an ionic bond. So on the picture, we have something like sodium chloride. Now, the ionic bond is very, very strong. So if I wanted to melt a solid salt like sodium chloride into liquid molten salt, I would need a whole lot of heat to do that, to break that attractive force so it could melt into a liquid. So now we just want to look at the relative strength of these forces. So my intermolecular forces, those are the forces between molecules, those are always going to be weaker than my intramolecular forces that are within molecules. So my weakest is dispersion. Dipole-dipole is a little stronger, and hydrogen bonding is a bit stronger than that. There's another one on here, ion dipole, that we didn't talk about, but there are many, many different types of intermolecular forces. What you have to understand is that these are the forces of attraction that hold together substances. So ion dipole, an example of that would be like salt water. So the ions from sodium chloride would interact with the dipoles on water molecules. This is why salt water has a higher boiling point and a lower freezing point than pure water. It's why we put salt down on ice in the winter. So my intramolecular forces are going to include ionic bonds, which tend to be stronger than covalent bonds. If you think about a covalent bond versus ionic bond, an ionic bond is going to be really hard to break. Okay, so intermolecular forces matter because they impact the state of matter. So our state of matter could be solid, liquid, or gas. The molecules of each state attract each other, and the force of attraction increases as the distance between molecules decreases. So in other words, the closer together the molecules are, the greater the force of attraction between them. So when liquid water evaporates into gaseous waters, are there any bonds between hydrogen and oxygen being broken? So we see that that's not the case. We have H2O liquid, and we have H2O gas, but both of them are still H2O. So we haven't broken any chemical bonds. Instead, what we've changed are the intermolecular forces. So intermolecular forces are much stronger in liquid because the molecules are closer together and they can interact more. In gas, those particles are really far apart. Those molecules have lots of space in between them. So, how do you go from liquid water to gaseous water? You have to boil the water. So you add heat to do that. So by adding heat, we're really breaking up those intermolecular forces, allowing my liquid to boil into a gas. So let's take a look at question 3. Here we have a water molecule and a hydrogen sulfide molecule. So looking at these pictures, we see that they look very similar. And that's because oxygen and sulfur are in the same column on the periodic table, so they're going to have very similar properties. So first we want to figure out my intramolecular force. So let's figure out if this is ionic or covalent. I've got hydrogen, oxygen, and sulfur. Those are all nonmetals. So neither of these can be ionic because we don't have any metals. We don't have any polyatomic ions. So then they're covalent. The question is, are they polar covalent or are they nonpolar covalent? So a quick way to test is if you can cut it in half in any way and it's asymmetrical. So that looks pretty symmetrical, but if I cut it in half like this, it looks pretty asymmetrical. So for both of these, because of their asymmetry, they're going to be polar covalent. So now let's talk about the intermolecular forces that are present. So the weakest we have on here is dispersion. This happens in all molecules. These are both molecules, so they both have dispersion. Both of these molecules are also polar, so they've got dipole-dipole forces as well. In order to hydrogen bond, we need a hydrogen attached to an F, O, or N. So we see that in water, but we don't see that in hydrogen sulfide. The last one on here is ion dipole. We would need to have an ion in addition to a polar molecule. We just have polar molecules here, no ions. So neither of them have ion dipole. So one of these is a liquid at room temperature, and the other is a gas. So which one will it be? So whichever one is going to be a gas is going to have weaker attractions. So if we look at a gas, that should have weaker attractions in it. H2S cannot hydrogen bond, whereas H2O can, meaning that it's going to have weaker attractive forces. So of those two molecules, we would predict that H2S is going to be a gas. And in fact, at room temperature, it is a gas. Okay, so I would like for you to go ahead and pause the video and see if you can work through the next set of questions. And when you're ready, you can return to this video to check your work. So on this slide, it seems that my pictures have left, so I'm just going to draw in my Lewis diagrams real quick. Okay, so neither of these are ionic compounds because they're all made of non-metals. The question is, are they polar or are they non-polar? So methane, if you cut this in half, it pretty much looks symmetrical no matter what way you do that. So this is going to be non-polar covalent. Methanol, on the other hand, is very asymmetrical. So methanol is going to be polar covalent. So let's talk about the intermolecular forces here. They're both molecules, so they automatically have dispersion. Methanol is polar, so it's going to have dipole-dipole. Methane is nonpolar, so it does not have dipole-dipole. Methanol also has a hydrogen attached to an oxygen. This means that methanol can hydrogen bond. Methane cannot. And neither of them have any ions, so there's no ion dipole forces here. So why is methane a gas, but methanol is a liquid? So methanol can hydrogen bond, and these stronger attractions make methanol stickier than other molecules, than our methane, holding them close together as a liquid. So methanol is going to be a liquid at room temperature because it has stronger intermolecular forces holding it together as a liquid. So surface tension is a measure of how strongly attracted molecules within a liquid are to each other. This means the stronger the attraction between molecules, the higher the surface tension. So surface tension is what's used by like insects to be able to walk on water. And it's because when you look at the surface of a liquid, that liquid is more attracted to itself than it is to the air. So when examining a bead of water on a car, the attractions between the water molecules are much stronger than the attraction of the water molecules to the car surface or to the air. So this means that water is going to form beads rather than spreading out. So go ahead and pause the video and follow the directions to complete the next set of questions. Return here when you are ready to check your work. So we're going to place 1 drop of isopropyl alcohol and 1 drop of water onto the desk. Based on your observations, which substance will have stronger intermolecular forces? So when you put the alcohol onto the desk, it's going to kind of tend to spread out into a puddle, whereas your water is going to tend to form nice round little beads here. So that's because the strong attractions between water molecules are going to hold those molecules close together. In alcohol, they're going to spread out because those molecules are less attracted to each other. So intermolecular forces also impact phase changes. So it impacts the state of matter, it impacts the surface tension, it also impacts how easily a substance will phase change. So evaporation occurs when the attractive forces between molecules are weakened enough that molecules can escape the liquid phase and enter the gas phase. So I want you to go ahead and pause the video and take some time to answer the next couple of questions. Return here when you are ready to check your work. So we're going to push those 2 streaks, those 2 drops from question 7 into 2 streaks of liquid. And we want to see which one evaporates more quickly. So the isopropyl alcohol is going to evaporate faster. Now in question 7, we said that the water is going to have stronger intermolecular forces. So isopropyl alcohol has weaker intermolecular forces. This agrees with our observations about which one evaporated more quickly because the isopropyl alcohol evaporated first. This means that there are weaker attractions holding the isopropyl alcohol together as a liquid than the attractions within water. Now, interestingly enough, both water and isopropyl alcohol can form hydrogen bonds. So let's see how many each one can form. So I've got 1, 2, 3, 4 for H2O, and only 1, 2 for isopropyl alcohol. So that means that water is better at forming hydrogen bonds. So water is going to evaporate a lot more slowly because it has more hydrogen bonds. So it will take more time for water to evaporate than it would take for the alcohol to evaporate. So go ahead and pause the video and spend a couple of minutes to work on the next couple of questions. Return here when you are ready to check your work. So we want to revisit the comparison between methane, which was this guy, and methyl alcohol. So that was this guy. And so we determined that methane was a gas. It had only dispersion forces, whereas methanol is a liquid. It has dispersion forces, dipole-dipole, and hydrogen bonding. So one of these substances has a boiling point of 65 degrees Celsius, and the other boils at negative 161.5. So which one is which? So methanol is going to have a higher boiling point because it has all 3 intermolecular forces. So it takes a lot of heat to weaken those intermolecular forces to the point where the liquid can turn into a gas when it can boil. Methane only has dispersion forces, so it's easier to boil. This makes sense too because the methane is a gas at room temperature. So it's going to have relatively weak intermolecular forces that allow it to be a gas at that temperature, whereas methanol is a liquid. Another way that intermolecular forces impact substances is through their volatility. So highly volatile substances easily evaporate because they have weak attractive forces between them. These compounds will usually have a strong odor. So for example, vinegar contains the molecule acetic acid, which is a volatile compound. So this means that the vapor, the air above the vinegar, is going to contain a lot of acetic acid molecules. And if you sniff this vapor, you will collect those acetic acid molecules in your nose, and you will experience the kind of sour, pungent smell of vinegar. So we want to look at these substances and determine whether or not they are volatile. So first one we have is sodium chloride. So sodium chloride is a metal and a nonmetal, making it ionic. So it's not going to have any of these intermolecular forces because we don't have any molecules. So intermolecular forces are going to impact molecules. Water is polar covalent, and it has hydrogen bonding, dipole-dipole, and dispersion. Salt water, the salt is ionic, and water is polar covalent. So we have all three from water, plus we have ion-dipole interactions. Next up, we have ethyl acetate. So ethyl acetate is made of nonmetals, and it's a bit asymmetrical, so it's polar covalent. If we have methane and water, those are both polar covalent molecules. So ethyl acetate has all three intermolecular forces. It does not have ion-dipole because there's no ions. Same thing for ethyl acetate mixed with water. So the difference is ethyl acetate is much more volatile than ethyl acetate with water. So when you smell the ethyl acetate, it's going to have a much stronger odor. It's going to be more volatile. So both ethyl acetate and ethyl acetate mixed with water are volatile, but when it's mixed with water, it's less volatile because those attractive forces are a little bit stronger with the addition of the water. And so we are able to have stronger attractions. It's less likely for anything to evaporate. I have a little error here. Ethyl acetate does not have hydrogen bonding from its molecule here because we don't have an H attached to an F, O, or N. It is possible for, say, one of these hydrogens to attract to this oxygen, but it's not going to be as strong as like a true hydrogen bond. When we think about sodium chloride is really not very volatile. It doesn't easily become a gas. Water, I would say, is somewhat volatile. It's not very volatile, but it does evaporate. Salt water is also going to be volatile, but it's less volatile than pure water because we have these additional ion-dipole forces here. That makes the attractive forces a little stronger, so salt water would be a little less volatile than pure water. So for Journal Write 5, we want to explain your observations about the vitality of substances in terms of the intermolecular forces that are present within each molecule.